Let us discuss few applications of the integral mass balance equation. Each application we will highlight one aspect. First is a mass balance for a thickener, which is a typical process calculation example. The whole idea is to show that what we had done earlier is use the equation which I derived now, so that you do not think they are two different things. Okay. Second example is a mass flow at a pipe junction, case where you have multiple inlets, multiple outlets. Okay. Third example is flow through a flat channel, our well known example. Here the aspect which we pay attention is that the velocity is uniform at the inlet, but the velocity is not uniform at the outlet. So, how do we take that into account? And all these three cases, the first three cases are for steady state operating condition. Fourth example will be considering the transient as well. We have a tank which vents out, how the density varies as a function of time. Okay. So, first take an example from process calculation. Once again like to emphasize that all the examples in your process calculation course where you would have done total mass balance falls under this category. You would have come across this term integral balance and integral mass balance in a process calculation course. Now, you really understand what was really meant by the term integral balance in the process calculation course. Okay. Probably that time you would have not paid attention, but now you know what is really the meaning of that, what is a full fledged equation, after many simplifications how does it get to the equation of process calculation book, etc. Okay. We take a very specific example here, a thickener in a waste disposal unit of a plant removes water from wet sludge as shown in figure. So, in this figure you see 100 kilogram of per hour of wet sludge entering, some amount of water is removed per hour, the dehydrated sludge flow rate is given, which is 70 kg per hour. Okay. So, how many kilograms per hour of water leaves the thickener per 100 kg per hour of wet sludge that enters the thickener? The process is in the steady state. As we discussed some time back, all the values are given in terms of mass flow rates directly, okay, not in terms of velocity, densities, etc. Okay. Okay. So, let us write the general integral total mass balance equation which we derived to begin with. Okay. Rate of change of mass in the control volume plus net rate of mass leaving the control volume to the control surface equal to 0, and then we simplified it. We made a lot of assumptions. All the assumptions are, we make assumptions relevant to the problem at hand. First is steady state, and then we assume that the velocity is perpendicular to area, and then density and velocity uniform across area. Then we could write in terms of the mass flow rates. This first term represents transients of 0. This net mass flow rate leaving is written in terms of total mass flow rate leaving minus total mass flow rate entering. Okay. So, let us apply this equation for this example. You have two outlet streams, one through which water leaves, other through which the dehydrated sludge leaves. So, for this term we have m dot of water, mass flow rate of water, plus mass flow rate of dehydrated sludge, and then minus we have one inflow which is the wet sludge. So, minus mass flow rate of wet sludge. Okay. And let us substitute the known values. We are given the mass flow rate of dehydrated sludge, which is 70. We are given the mass flow rate of wet sludge, which is 100, and this has to be found out. So, if you solve, you will get 30 kg per hour. This problem is very simple. The idea of showing this example is, once again I repeat, to relate the equation which you would have started off in the process calculation course This would have been your starting point in a process calculation course, or straight away you would have written this equation. We are just showing that this equation is a very simplified version of the general integral total mass balance equation. Of course, 30 kg per hour of water leaves the thickener. Okay. Let us move on to the next example, which is mass flow at a pipe junction. We consider the steady flow in a water pipe joint shown in the diagram. You have a pipe here, another pipe here, another pipe, it is a pipe junction, okay. And the areas of them are given, the cross sectional areas are given. A1 is 0.2, A2 is 0.2 meters squared, and A3 is slightly less, 0.15 meters squared. Okay. And then you have a, let us say, a leak or a small hole through which water is lost. In addition, fluid is lost out of a hole at 4, I mean the location 4, estimated at a rate of 0.05 meter cube per second. Because it is a leak, it is a small hole, it may not be regular also. So, usually you know the volumetric flow rate through that. Okay. That is why volumetric flow rate is given, you are not given velocity through that hole or area of that hole. If it is a well defined inlet or outlet, etc., then you know the area, you define in terms of velocity. It is a small hole and a small leak over it, then you do not specify in terms of area and velocity, just in terms of whatever is leaking out in terms of, let us say, flow rate, volumetric flow rate. Then you are given the average speeds at sections 1 and 3. So, this section 1, the velocity is 5 meters per second, and section 3 a high velocity of 12 meter per second. Okay. It says average speed because we are not considering variation across the cross sectional area. So, we just give an average value, that is why it says average speed at sections 1 and 3. Okay. And we are asked to find out what is the velocity at section 2. To begin with, we say that water enters at section 1, leaves at section 2 and leaves at section 3. We will have to verify based on the result what we get. Okay. Let us see what happens. Okay. Now, let us start with the general form of the integral mass balance equation. We will make a set of assumptions, steady state, okay, and velocity is perpendicular to area. So, across all the phases, let us say this velocity and this area perpendicular to each other, similarly at the other phases as well, other inlets and outlets as well. And then the density and velocity are constant across the cross sectional area, okay, which we have done several times. So, if you make these assumptions, this integral balance equation gets simplified to this equation. This transient term is 0. Now, unlike the previous example where this equation was written in terms of mass flow rates, same equation now has been written in terms of densities and velocities and areas. As I told you, that is more a practical way of representing the conservation equation, because those are the measurable values, measured values. Okay. And this is a good example where the specifications are as close to as possible to the reality, meaning you measure velocity, measure area, etc. That is why instead of writing m I dot, m I dot, etc., I am writing in terms of rho I, V I, A I. Okay. V I is the magnitude of velocity, as we have seen earlier. Okay. So, let us write down this equation for this pipe junction. In terms of outlets, we have considered 2 to be a section 2 to be outlet, okay, and section 3 to be outlet, and 4 is also outlet, and there is only one inlet, which is section 1. Okay. So, let us write down that because it is water, I kept the density to be constant. So, I use just rho instead of rho subscript 1, 2 or 3 or 4, etc. So, this has been expanded for the outlets. For outlet 2, it is rho and then V 2 A2. Similarly, for outlet 3 and then outlet 4, right now it is rho V 4 A 4. Let us see how do we substitute, and then minus, there is only one inlet. So, rho V1 A1 all represents the, all terms represents the mass flow rate, either leaving or entering respectively. Okay. Now, we will substitute the values. We are given the values of A1, A2, A3. We are given the velocities, V1 is known, V3 is known, V2 has to be found out. And then we are given the, we are not given V4, A4 etc. We are given the product V4, A4 as we have mentioned few minutes back. We are given the flow rate, volumetric flow rate, not mass flow rate. Okay. Okay. In this equation, rho cancels out, okay. It is constant. So, then let us substitute all the values. V2 is to be, has to be found out, area is 0.2 and V3 is 12, area 0.15, V4 A4 is 0.05. Okay. V4 is and A4 are not given separately, product of V4 A4, the volumetric flow rate is given to us. So, V4 A4 is 0.05 and of course, minus sign, and V1 is 5 and A1 is 0.2. Now, if you solve this equation for V2, you will get minus 4.25 meters per second. Okay. As I told you, to begin with, we assumed that water is leaving through this phase, and so we included that in the outlet as a flow rate leaving the control volume. Okay. But now we have found out that V2 is negative, which means that water is entering through the inlet 1, water is also entering through this surface 2 and leaving through this outlet surface 3, and of course, leaving through outlet the whole 4. That is why the velocity V3 is much higher. So, entering at through one inlet at 5 meters per second, through the other inlet at 4.25 meter per second, leaving at 12 meters per second. Okay. Both the, and the cross section area is also less, so resulting in a higher velocity. Okay. So, this good example where we work in terms of velocities, areas and then apply the integral mass balance equation. As is mentioned in flow at section 2. Okay. Okay. This example is to illustrate the use of velocity profile. If we have so far assumed that the velocity is uniform across the cross sectional area of the inlet or outlet. Suppose if the velocity varies across the inlet or outlet, how do we take that into account? Remember the equation what we have derived can take this into consideration. Okay, let us read the example. Water enters a wide flat channel of height 2h with a uniform velocity of 2 meters per second. This geometry is very well known to us and which is shown here, and the inlet velocity is 2 meters per second. Remember, understand the word uniform velocity. What does uniform velocity mean? The velocity does not vary over the height of the channel. Over this height, the velocity does not vary at the inlet. Okay. Okay. At the channel outlet, the velocity distribution, meaning velocity varies along the y direction. This is the y direction. Okay. Along the height of the channel it varies, and we are given the velocity profile. It says Vx because velocity in the x direction, okay, and that is a function of y. Velocity in the x direction varies in the y direction, okay. And Vx max is the maximum velocity which are supposed to find out, okay, where y is measured from the center line of the channel, this center line of the channel. So, y is measured. So, for example, if 2h is the height of the channel, y is plus h here and then minus h here. Okay. Okay. That is why we are given the position of the coordinate axis, y starts from the center line axis. Now, we are asked to find out the determine the exit center line velocity. Velocity is maximum at the center line. So, we are asked to find out what is the exit center line velocity Vx max. Why is it center line? When you substitute y equal to 0 in this equation, you get Vx equal to Vx max, that is why center line velocity. Okay. Now let us start with the equation, the most general form of the integral balance equation. We will make some assumptions, but not all of them. Steady state, velocity is still perpendicular to area, though the velocity either the inlet or the outlet. In the inlet the velocity is uniform across the area, but still perpendicular to the area. In the outlet it varies across the channel height, but still it is perpendicular. So, at the inlet it is uniform throughout, it is perpendicular. At the outlet it varies, but still it is perpendicular to the area. So, this assumption is valid. And now in the earlier examples we took the density and velocity to be uniform across the area. In this example we are taking only the density to be uniform across the area. We are not taking as that the velocity is also uniform, which is not valid at the exit. Okay. Now, when you simplify, the equation just becomes integral rho v dot and dA equal to 0. The first term, the unsteady term does not contribute. Okay. So, now let us split this term for the control surfaces 1 and 2. The inlet is denoted as control surface 1, outlet as control surface 2. Okay. So, what I have done here, I split this control surface as control surface 1 and control surface 2, and of course, right hand side is 0. Wherever there is a wall, velocity 0 does not contribute. Okay. Now, we will have to find out expression for this for the inlet and outlet. For the inlet, let us express this for the inlet. Rho is a constant I have taken here. Now, V dot n, remember it is an inlet, it is negative. So, I have negative sign here, and minus the magnitude of velocity. What is the magnitude of velocity? It is V in. Okay. And then what is this area? The velocity is constant across the entire area. What is the area we should take? We have flow between the two parallel plates. So, the cross sectional area of flow is this cross sectional area of flow, and that is what is shown here. So, the area of cross section for the flow is the width of the plate is shown here as W. The distance between the two plates is 2h. So, W into 2h is the area through which water flows inside. So, when I take rho into V dot n constant outside, I have integral dA, which is A, which is 2h into W. I will repeat quickly. Rho is constant taken out, V dot n is minus V in, that is also taken out because it is constant across the area. So, I am left with integral dA, which is A. What is the area? Water flows in this direction. So, this area, let us say you look from the side view, and that is what is shown here. So, area is W into 2h. So, substituted at 2hw. Now, let us take the second term. We have rho which is written as such. Now, V dot n is positive because flow is leaving the control volume, and what is the velocity now? It is Vx as a function of y. Earlier Vn was just a constant, but now Vx, to be more explicit, we also mention Vx as a function of y. Okay. Now, what is the area we should take? Okay. In the this is the outflow, the side view is shown here, and the width is still W, but now because velocity varies along the y direction along the height, I cannot take the entire 2h, I take a small strip of height dy. So, area of this strip is dy into W. So, that area is denoted as dA, which is dy into W. So, the area dA here is dy into W. Why do we do this? Because the velocity varies along the height of the channel along the y direction. So, I cannot take the entire area W into 2h, I only take a strip which is of height dy, so that then I integrate to cover the entire area. So, dA is equal to dy into W. Okay. So, the second term we have rho and outflows are positive, and the magnitude of velocity is Vx, it is a function of y, and area as dy w. Okay. So, let us see, let us continue with this in the next okay, rewriting the same equation here. Okay. So, now we are given the velocity as a function of y. Okay. Okay. W cancels out in the in this equation, and let us substitute for V x as a function of y from the given velocity distribution. So, cancelled out W here, substituted cancelled out rho as well, that also cancels out, and substituted V x in terms of the velocity distribution. Now, let us rearrange this equation and do the integration as well. This equation has been integrated, V x max, that is a constant, integration of this term gives you y, integration of this term gives you 1 by 3 y cube by h squared. Now, coming to the limits, first we said the limits was in terms of control surface 2. Now, the independent variable is y. So, the limits are written in terms of y, and the y value varies from minus h to plus h, because y equal to 0 represents central line, and we substitute those limits here. Okay. Okay. I take to the right hand side, so it becomes 2 h v n. Okay. Now, substitute the limits, and then once you evaluate this equation, this entire term, all these terms get simplified to just 4 by 3 h, and right hand side you have 2 h into V n, of course, you have V x max. If you simplify, you get V x max is equal to 3 by 2 V n. What does it mean? The maximum velocity is 1.5 times the inlet velocity. The inlet velocity is given as 2 meters per second. You can find out what is the maximum velocity at the exit. Okay. So, good example where at one inlet it was uniform velocity, and the outlet the velocity varied across the cross section area. By using this integral sign, we have been so far telling that integral sign accounts for variation of velocity density. It is a good example to demonstrate that as well. And you also see that if you have such a situation, the maximum velocity is 3 by 2 times the inlet velocity. The last example where our attention is to consider a case where there is transient, whereas unsteady state, that is the focus of this example. Let us read the example. A tank of 0.06 meter cube volume contains air at 800 kilopascal absolute and 15 degree centigrade. Okay. So, given the volume of the tank, you are given the pressure and temperature, and at time t equal to 0, air begins escaping the tank through a valve, and with a flow area you are given a small area 65 millimeters squared. Air passing through this valve has a speed, you are given the speed as a very high speed of 300 meters per second, because high pressure and it is a small area as well, and the density of air leaving is 6 kg per meter cube. Okay. Determine the instantaneous rate of change of density in the tank. Rate of change of density tells you that it is d rho by dt. That rate keeps changing because as air escapes, the pressure inside falls, okay, and the velocity can change, the density can change. So, whatever you are finding out is instantaneous rate of change of density at time t equal to 0. Moment you open the valve, how does the density change with time? That is why it says instantaneous rate of change of density in the tank. Moment say instantaneous, you mention a time, and that time is t equal to 0. Moment you open the valve, what happens? Okay. Now, let us start once again with the most general form of integral mass balance equation. For all the earlier examples, we assumed steady state. So, this term is always 0. Now, we cannot do that, it is a transient case. So, that assumption is not listed here, all other assumptions are listed. Now, because we are going to consider the accumulation term, that a transient term, we need to make another assumption that the density is uniform inside the control volume. No longer we, so far we need not mention that, because that term was anyway 0, but now that term is going to contribute. So, now we should say whether rho is varying within the control volume or it is a constant within the control volume. That will enable us to take out whether should we keep it inside or can I take it outside. As usual, to simplify the analysis, we will say rho is uniform inside the control volume. Okay. And then of course, velocity perpendicular to the area, when it leaves we are saying velocity is perpendicular to the area at the outlet, and then rho and velocity uniform across cross sectional area, we are not considering any variation across the cross sectional area. Okay. So, these assumptions are made depending on what aspect we are trying to focus on a particular problem. Okay. Now, so now the first time we are including the transient term d by dt of rho v. Of course, these terms are very familiar to us, total mass flow rate leaving, total mass flow rate entering. Now, in this derivative, remember this was obtained by assuming rho as constant. So, that is reflected here. Now, within this derivative we have two variables rho and volume. The volume of this control volume, the tank is a constant, it is a rigid volume. So, I can take V to be constant, so that I can take this out of the derivative. Okay. And then there is no inflow at all, there is no inflow obviously, there is only outflow, there is only outflow. So, this term will not contribute, there is no inflow, only outflow will contribute, and there is only one outflow. Okay. So, let us see, I have taken out V, then I have d rho by dt, and then there is only one outlet which I denote as 1 section 1. So, rho 1 V 1 A 1 is equal to 0. So, equation becomes much simplified, because we have only one outlet, but of course, there is a transient term there, okay, which is d rho by dt. Okay. So, let us simplify this equation. What is required is instantaneous rate of change of density. So, let us keep that on the left hand side and rearrange for d rho by dt as minus rho n V 1 A 1 by V. This represents velocity, the magnitude of velocity, this represents volume of the tank. Okay. Let us substitute all the values. The velocity is the density of the stream leaving the tank was given as 6 kg per meter cube, and the velocity was given as 300 meters per second, and the area was 65 millimeter squared represent in terms of SI units. Okay. The volume is 0.06 meter cubed. So, this gives you the rate at which density keeps changing. Of course, obviously it should decrease, because air escapes, and how does it decrease? Roughly at the rate of 2 kg per meter cube. Okay. So, the density is decreasing at this rate due to escape of air. Okay. Once again, a very simple example to demonstrate the unsteady state term, all others are something known to us from the previous examples. Okay. To summarize the conservation of mass part, the total mass balance part, the integral mass balance alone. Okay. Okay. So, the law of conservation of total mass for a system is started from that and express that in terms of the integral total mass balance equation for a control volume, okay, using Reynolds transport theorem. With that objective, we derive the Reynolds transport theorem. We have seen the first application of Reynolds transport theorem. Conservation of mass for a system, the law of physics, has been expressed in terms of a governing equation as a conservation equation, but in integral form for a control volume. We use the Reynolds transport theorem for that. Okay. We will see several applications of that for other properties as well, momentum, energy, and then species mass. Okay. Now, the integral total mass balance equation, what we have derived is more generic than the integral total mass balance equation used in the process calculation course. What are they? Transient unsteady state term, inflow outflow across any part of the control surface, then any angle between velocity and normal to surface, and of course, density velocity can vary across the surface. Okay. And looked at applications of this integral total mass balance equation, process calculation example, an example with multiple inlets and outlets, example considering velocity profile, an example where we included the unsteady state term.